So let me guess, you've done the work, right? The late nights, the leak code grind, you feel like you know the stuff. But then you walk out of that interview, no offer, and you're just left wondering what went wrong. Well, here's the secret, and it's a big one. It's almost never about you not being smart enough. It's about falling into a few hidden but totally avoidable traps.
And this is the question that just drives you crazy, isn't it? You've put in all those hours, you know your big O, but the result? It just doesn't match the effort. And that frustration? It's totally real. But here's the thought. What if the fix isn't about learning some crazy new algorithm? What if it's way simpler than that?
And that right there is the key. That's the idea we have to get into our heads. Acing these interviews, it's not about some flash of genius. It's not a test of who can invent a brand new algorithm on the spot. No, it's a test of execution. It's about solid professional engineering, recognizing the patterns, writing clean code, and just skillfully avoiding the common pitfalls that trip up even the smartest developers. All right, so to help you navigate all this, we've broken these mistakes down into 3 big categories. Think of it like this. First, we've got strategic blunders. These are the mistakes you make before you even type a single character. Then, there are the implementation pitfalls, those sneaky little bugs that can wreck a perfectly good idea. And finally, the analysis blind spots, where you might make the wrong claims about how good your code actually is. Let's dive in and tackle them one by one.
Okay, category 1, strategic blunders. Now listen up, because this is where interviews are often won or lost. I mean literally, before you've even written a line of code. The choices you make in that first minute, that first 60 seconds of looking at a problem, can set you on the path to an amazing solution, or, well, a complete dead end.
All right, the single biggest strategic mistake? It's ignoring the input constraints. Seriously, just look at this table. It's basically a cheat code for your interview. If the interviewer says n can be up to, say, 100,000, your brain should immediately be screaming, no nested loops, no way. Why? Because an O n-squared solution is going to time out for sure. The problem itself is practically yelling at you, telling you that you need something in the O(n) log n or O(n) family. Think sorting, think hashing. Okay, next up. Picking the wrong tool for the job. It's a classic blender. Think about it like this. If you need to check if a name is on a guest list with 1,000 people, you wouldn't start at the top and ask every single person one by one, right? That would be crazy. But that's exactly what you're doing when you use a list for a membership check. That's an O of n operation. Instead, you'd use an index, a directory. And in our world, that's a hash map or a set. We're talking about the difference between a painfully slow scan and a near-instant O of 1 lookup. It is a massive, game-changing difference.
And when it comes to graphs, oh boy, this is a classic trap. The interviewer says, shortest path in an unweighted graph, and your muscle memory just jumps to DFS. But hold on, DFS is great, but it's an explorer. It just wanders. It might find a path, sure, but it could be this long, winding, scenic route. BFS, on the other hand, is methodical. It's like ripples in a pond. It explores all the neighbors 1 step away, then 2 steps away, and so on. It guarantees, absolutely guarantees, you will find the path with the fewest edges every single time. All right, so let's say you nailed the strategy. You picked the perfect algorithm, the best data structure, you're feeling good. But now you actually have to code it. And this, my friends, is where a brilliant idea can get totally derailed by tiny, sneaky bugs in the implementation. Binary search. The absolute poster child for an algorithm that sounds so simple on a whiteboard, but is just notoriously tricky to get right when you're coding. Come on, we've all been there, right? Stuck in that dreaded infinite loop or your pointers are off by just 1, missing the target. Heck, even the simple act of calculating the middle index can cause an integer overflow with big numbers. These tiny little bugs can completely sink an otherwise perfect approach. So how do you actually avoid these bugs? Well, let me share a pro-level technique with you. Defining a loop invariant. Now, I know, it sounds super academic and complicated, but it's not. It's just a simple promise that your loop has to keep. That's it. Before you even write the loop, you state a rule that must be true at the beginning and end of every single iteration. For our binary search example, that promise could be something like, the target I'm looking for, if it exists, is always somewhere between my low and high pointers. If you write your code to keep that promise, guess what? Those nasty off by 1 errors, they just vanish. It's an absolute game changer for writing correct code when you're under pressure.
And of course, we can't talk about implementation without talking about edge cases. A great idea is worthless if it crashes on simple inputs. So you have to ask yourself, what happens if the array is empty? What if there's only one element? What if all the numbers are duplicates? A really solid, robust solution handles all of this stuff gracefully. And you know what? Thinking about these cases out loud in front of the interviewer, that doesn't just stop your code from crashing. It shows them you have the mindset of a real professional engineer.
Okay, you've done it. You have a working solution, it passed the edge cases, you're feeling pretty good, but you are not done yet, not by a long shot. The final part of the interview, analyzing your code's performance, this is where the very last set of hidden traps are waiting for you.
I'm sure we've all heard this one before. Maybe we've even said it ourselves. You write a nice recursive solution and confidently say, my solution uses O1 space. I mean, it seems to make sense, right? You're not making a new array, you're not building a giant hash map, so the space has to be constant. Well, this is one of the most common and honestly, one of the most revealing blind spots in complexity analysis.
So here's the deal. The crucial thing to understand is the difference between input space and auxiliary space. Auxiliary space is any extra memory your algorithm uses up. And here's the kicker. The part everyone forgets, the function call stack absolutely 100% counts. Every single time a recursive function calls itself, a new frame gets pushed onto that stack. It's got to store local variables, its current state, and that stack takes up real space.
And this is a perfect example. The iterative version of binary search, the one with the while loop, it just needs a few variables for pointers. That is true O of 1 auxiliary space. But the recursive version, that call stack is going to grow. It'll grow to a depth of log n. So you've got the same algorithm, same time complexity, but a totally different space complexity. Knowing this distinction is absolutely critical.
And here's another one. This is a blind spot that really separates the good candidates from the great ones. Just assuming that hash maps are always O of 1. Look, we love them because on average, they are lightning fast. But a great engineer always thinks about the worst case. What happens if you get a terrible hash function and tons of keys all pile into the same bucket? All of a sudden, your beautiful O of 1 lookup just turned into an O of n slog through a linked list. Just mentioning that you understand this trade-off, that shows your interviewer a whole different level of understanding.
Phew. Okay, so we have covered a lot of ground. We've identified the major traps in strategy, implementation, and analysis. So now let's pull this all together. Let's create a simple, actionable checklist you can literally use to structure your thinking in any interview.
This right here, this is your new framework, your secret weapon. Every single time you get a problem, just mentally run through these 5 steps. 1. Read the constraints. Figure out your target complexity. 2. Pick the right data structure for the job. 3. Use invariants to write bug-free code. 4. Analyze both time and auxiliary space. Be honest about it. And 5. Handle all those tricky edge cases. If you follow this process, you're not just coding, you're engineering, and you'll systematically avoid every single trap we've talked about.
See, by turning these common mistakes into a conscious checklist, you're not just crossing your fingers and hoping to avoid traps anymore. No, you're following a clear map that leads directly to a great solution. So as you go from here, I want you to ask yourself, which one of these hidden traps are you going to focus on fixing first? Is it your strategy, your coding implementation, or your analysis? Pick one. Make that your focus. And that's your very next step to absolutely acing that next technical interview.